How do I know that this has been? Okay. Yes, now we have only have 15 students. We wait for another 2 3 minutes. I'm going to share my slide. 16 students. No worries. So I can track your attendance by activating the Google Meet attendance. And so I don't have to take the call your names. So I just based on the attendance that will be generated after our session. So see each after each our session there will be an Excel generated, so I can trace who are in there. How long have you been in the class? I can track your attendance. Right. Okay, so we have 16. Again, make sure that you uh, attend not less than 80%. Okay, so if you're less than 80%, your name will be sent to the school, the engineering, the I'm not sure, the academic office, and there will be a letter or you'll be called for anything. Right, so I'm not going to let that happen, and please make sure that you attend. Yang lain mana ni? Masih tidur ke apa? Another 5 6 students. Okay. So please give them a call. If you can WhatsApp them and make sure they attend it. Right. Okay. So we are in week 4. Okay, week 4, and we should have started the DC drive, but I have yet to complete. So inshallah, by today we're going to complete the activities. By today we're going to complete this electrical braking, DC steady state multi-quadrant operation with phase converter and chopper. Okay, we're going to complete that inshallah. Next, this Friday we're going to start on the DC drive. Right, this Friday we're going to start with the DC drive. I believe this is again will be a long weekend. Some of you may follow your parents. You have a long weekend, so no worries. We try to have a short video, a short class this coming Friday, right? And we start on the DC drive. Okay, right. So we come back to the note. Close this, and we stop last week, last Friday. This regenerative braking. Is that true? Regenerative braking? Yes. Okay. So we come back to we reverse back on the braking. So again, in DC drive, the braking is the one of the important elements that we need to look at. Right, braking. This is not normal braking system whereby you have a disc brake. You have a disc brake. You have a, if you apply for a vehicle, this is not the normal braking. It's not manual braking, but we talk about the electrical braking. Electric braking. Right. So we have three types of braking. The first one is known as regenerative braking. The second one will be dynamic or rheostatic braking. And finally, you have the counter current braking. Or there are two techniques in counter current braking. One is the plugging, the other one is reverse voltage terminal. Right. Regenerative braking. Talk about that. Brake pad, brake rotors, everything. And then we have regenerative in most cars, but automotive engineers have given this problem a lot of thought. Regenerative braking. The system that drives the vehicle does the majority of the braking when the driver steps on the brake pedal of an electric. Already, these types of brakes put the vehicle into reverse mode, causing it to run backwards, slowing the car's brake wheel. By running backwards, the motor also acts. You can read that. Now I'm going to go back this. Okay, we're going to look at further on this, more deeper on this regenerative braking of DC shunt. So let's assume that we have a DC shunt motor. So how does the DC shunt motor take that? So you have DC shunt motor. You have example. Field winding. You have armature, resistance. This is the big back EMF connected in shunt. Then you connect straight back to your DC voltage rate. So this is the shunt motor. DC shunt motor. So in motoring mode, so you have a current IA, the terminal current. This is IT coming into the nodes here, and it is divided into IF and IA, the armature current. So the armature current will flow. So the armature current will flow into that direction. So we have IT equals to IF plus IA. Right. And next is that we have two conditions to explain in this okay, just click this, delete. Wait a second. Okay, this. Okay. Right. So we have uphill direction. Yeah. during this time, if you go uphill, there is a load torque, or we call it as a force, eh, that actually move towards downhill, isn't it? Eh? And we want the motor to rotate in that direction. Eh? So now we have this, and also we have the torque of the motor will follow the torque of will follow the direction of the car here, isn't it? Eh? So we are in actually in the motoring mode, right? But during the downhill directions, we have the same load torque or load force that is going downhill, eh? and we and the car also rotates in the same direction of the load. So if you think about without any force, external force, of course, this car will go over speed, isn't it? It will go over speed. So you need to apply a force, the opposite direction to the motor rotation or to the load torque, so that you're going to brake the motor here, isn't it? Right? So that is a basic. I mean the how the motor works. Now we're going to looking at, okay. In the downward direction, the speed of the bus may exceed its no load speed. So there is a no load speed here. We usually write as a omega naught. This is no load speed. Okay, this is no load speed. The speed of the bus may exceed its no load speed and hence generate electric power that can be pumped back to the source. Right? And let's go to the next slide. In the uphill direction, the DC machine acts as a motor. The load torque in this case is opposite direction. And the load torque, remember, I can uh, redraw here. So if you have your cars going up there, this is your wheel. The load torque is, in this case, the opposite direction of the bus motion. So we have, you want to move towards, and therefore your omega m is going in that direction. This is your omega m, and this is your Fm, right? Your motor force, and of course your load torque will be in the opposite direction. This is your Fm, load torque. The load torque in this case is opposite direction, and the drive system is in the first quadrant. First quadrant, isn't it? So I hope you still remember first quadrant. Whereby, if you can quickly draw, you have this as a torque, speed, and this is your torque, right? This is your first quadrant, second quadrant, third quadrant, and fourth quadrant. Okay, so you have your torque equals to the same direction of the omega. So both are positive. Both are positive. Right? Omega and also torque is positive. Right. The equivalent circuit of the system is shown. So this is a normal DC motor circuit, right? DC normal circuit. So you have first, the IA or the IT here equals to IA plus IF, right? And we have VT equals to EA plus IARA, right? And you have, if you rearrange, you have EA equals to VT minus IARA, and we know that EA equals to K flux omega M. And we also know that torque equals to K flux, the same K flux, same constant, multiplied by IA. Right? So this is the general equation. So if you rearrange, if you substitute the equation into that particular equation, then finally you have A equals to B T minus IARA. Now it's become this. So we have K flux omega m equals to B minus IARA. Therefore, you have omega m equals to Dt over K flux minus IARA over. Okay, this is the first equation. If you use, if you want to find omega m, and then you have this terminal voltage IARA, and that K flux. Okay, this K flux normally a constant. Why? Because flux, we know that flux come from the field winding, isn't it? Field winding. Okay, and normally flux is, we fix the current. IF is fixed by using, we call it as a variable resistor. So if you use a variable resistor, RF, then you can fix the IF. Okay, once you fix the IF, flux also will be fixed because flux is directly proportional to IF. And therefore, this equation can be replaced by, like, omega m equals to Vt divided by K, IA RA divided by K. Okay, so K equals to K flux. You can do that. And the other equation is, can I go to next grid frame? Step back down. Black again. So can I move back to? Great. So I can have all these notes. The kita punya drawing apa saya catat ni boleh pass to you. Okay, can pass to you, can share with you. So next we write back the equation omega m equals to Vt over K or K flux minus RA IA divided by K, and this also can be replaced by Vt divided by K minus, we know that torque equals to K flux, therefore we have, let me write this. Okay. Remember, torque equals to K flux IA. So if you replace that, then we have IA equals to torque over K flux. So you have RA torque divided by K flux squared. Right? So this is the two equations that you need to understand. Right? So we have omega m equals to, the first equation will be Vt over K flux minus IARA, and the second equation should be omega m equals to Vt divided by K flux minus RA torque over K flux squared. So that comes from torque equals to K flux. Here, so we have torque equals to K flux IA. Right? And so therefore these two equations, very important equation that you need to memorize. Next slide. Figure above shows that the speed torque characteristic of the DC machine. So this is torque speed characteristic of the machine. If you look further, if you can look at the the torque speed, right? So you have, okay, now if I cannot write here, so I have to redraw it somewhere here. I can draw it back. So this is a normal DC torque speed torque characteristic. So we have the normal operation at this point. Okay, point number one. Point number two here is where you have speed equals to torque equals to 0. So this is no load torque, no load speed. So this is omega naught, the point where we have torque equals to 0. Right? Then this is the first speed here, omega 1. You operate at uphill. This is during uphill. And this is downhill. And this is point 3. So if you look further, so this is your speed. Therefore, you can find out that omega 3 is slightly higher than omega naught, isn't it? Yeah? The speed during the downhill, when you try to change from, if you are at the top of the hill here, so if you start from there, so during here you don't have any movement. Omega m equals to 0, isn't it? If your car sit at the peak of the hill here, omega is 0. Eh? The speed is 0. The moment you move to the downhill, then your omega 3 here exceed the omega naught, which is known as the no load torque, no load speed here. So that's why a 3 is slightly higher than 2 and slightly higher than 1. So this is where you have omega 3. Okay. Right. So I'm going to share with you the solutions, some of the example to look at how we get that omega 3 and so on after the class. Okay. So that's the idea. Then we go further. Let's assume that operating point 1 represent Q1. So we have point 1 represent the Q1 uphill. So when the bus reaches the peak of the hill, the load torque seen by the motor is 0. So the load torque also equals to 0. At point 2, the operation robot is at the top of the hill. So here we have torque equals to 0. And this is also the point where you have torque equals to 0. It's not speed, but the torque. Sorry, I made a mistake here. So this is not omega is 0, but rather torque equals to 0. During the big bang. So this is the point we have, number 2. So therefore, if you look at this equation again, when the torque is 0, therefore omega naught only left what? Omega naught equals to Vt divided by K flux, since torque equals to 0. So by looking at this, consider that part, isn't it? So that part equals to 0, and therefore omega naught equals to Vt over K flux. Right? Okay. So if you want to find what is omega naught at the happy hill here, you can find from this equation. Okay, so next. Because the load torque at the top of the hill is 0, the armature current must also equal to 0. So we know that looking at the equation just now, if I may draw the shunt connection, so you have I C, you have IA going down here, and you have IF going down there. 3. So this is RA, and you also have RF. This is your EA, positive, negative. 3. Okay, so if you look at this equation, then you have IA2 equals to VT minus EA2 divided by RA equals to top divided by K flux, and this is equals to 0. So if you put at the A2, it is 0. Why? Because the top is 0. And there is no top, so IA equals to 0. In that case, if you have IA equals to 0, so therefore R equals to 0. Voltage drop across RA. So if I can write VRA equals to 0, isn't it? Because the current IA is 0. So VRA equals to 0. And therefore you find out that VT equals to EA. Whatever voltage, terminal voltage, also seen by the EA. So this is the point we have at the peak of the hill here. This operating point represents operation at point 2, which is the no load operating point of a DC. Okay, so I hope you can watch back this video and try to understand. Okay, so now assume that the electric pulse is traveling in the downhill direction, right? So after it stays that the heel, the peak of the heel here. Now let's assume that it start to move downhill. Okay, so what happened is the force is now change direction. Rather than going down on the left hand side here, going down the left hand side up downhill here, now it travels to the front of the car. So we have this is the back of the car, and this is the front of the car. So when it tries to go into downhill, now the load torques change direction from the rear, the rear of the motorbike to the front of the vehicle here. Okay, so the load torque in the downhill motion is reversed, and now it is in the same direction of the speed. So the torque now in the same direction of the motor. The motor speed will not change its direction. The motor will not change the direction. Doesn't change. It's still going clockwise. Isn't it? Still clockwise. And the motor moves to operating point 3. So now it moves to point 3. So just here. So now it operates under downhill operation. Okay, so let's try to get another set the background. Okay. So now we are considering downhill. So you have that. So, your car. So you're going to that particular FM. And now your motor also in that direction. Therefore, you have to apply FM. Okay. So the load torque in direction is reversed and the same direction. Note the motor speed will not change directions and move to a point 3. So if I can draw again, torque by the speed against torque. So we have point 1, point 2 uphill, peak of the hill, and now we have a downhill operation. So 1, 2, okay, right. Note that the motor speed change. Let's move on. In the downhill operation, the load torque changes its direction while the field current remains in its original direction. So we still have the same RF or IF going in that direction. So the magnitude of the field current is constant. We know that we fix the flux. So the field current is constant because the field voltage is constant. And hence, the armature current at point 3 must reverse its direction. Hence, the armature current at point 3 must reverse its direction. So instead of going down, now your armature current is going up. Right? Going up, and IA3 now is the same mission. So if I can write, so at point 3, So we have IA3 equals to load torque 3 equals to K flux. Okay, all right. Then we have IT equals to IA3 minus IF, or rather IA3 equals to IT plus IF. Okay, all right. The motor is now generating electric power and delivering to it. So in this case, now the motor, instead of having the power from electric to mechanical, now it transfers back from mechanical to electric. So it is a generating mode. The motor is experiencing the generating mode, and this is from the equation before, the motoring equation here. You have omega 3 equals to Vt over K flux minus Ra over K flux squared. Okay, TL3, which is this equation. Okay, that equation here, and IA3 equals to Vt minus EA3 over RA3. So this is still in the motoring generation, but now we know that torque is negative. Okay, so the torque is negative. So we have equation IA3 so we have equation omega 3 here. So you reverse, torque, now you replace TL3 equals to negative value, and therefore you have this equation omega 3 now become positive. Omega 3 equals Vt divided by K flux plus Ra over K flux squared multiplied by TL3, because TL3 is negative, and we also have the current IA3 equals to Vt minus EA3 divided by Ra, and this is minus torque L3 equals to Ra. Okay, that equation equals to minus torque L3 over IA. Yeah. So that's a bit of equation. We're going to look at the example afterwards. Okay, but that is a equation involved. Since IA3 is negative, so EA3 must be larger than VT. So we know that if I can redraw back, if I have my circuits again. Okay, so what does it mean here? Since IA3 is negative, because the current is reverse its direction, the IA is the reverse direction. So you must have EA here, the back EMF, greater than VT. Then you have this condition, isn't it? So EA should be greater than VT. Then you have that question. And now if you look at the speed against voltage of EA, the back EMF. We talk about the back EMF now. So during regenerative braking, so we found out that the EA is greater than VT. At this point, we have EA equals to VT, because IA equals to 0, isn't it? So EA equals to VT. So figure above shows the speed versus EA for all three operating points. So this is the motor operations, the speed against the generated EA, the back EMF. Okay. The machine acts as a motor when EA lower than VT in this case, but when because of the current flows in that the armature current is a reverse direction, then we have EA must greater than VT during this uh, regenerative braking. Okay, right. So this is again to look at the regenerative braking, which is we start from the motoring mode and we transfer to the generating mode. Sorry, braking mode, and this is known also regenerative braking. So look at the direction, the rotation of the torque, follow the speed or the rotation of the motor. In this case, and load torque is always opposed to Tm. This is during motoring, and once it goes into that regenerative braking quadrant, second quadrant, the torque now reverse opposite direction of omega, and we have the load torque rotate in the same direction of omega m. Okay, so this is regenerative braking. Okay, so we have done with the regenerative braking. Now we move into the dynamic. You can try that. Okay, now we move into the dynamic braking. Okay, right. So when an electric motor spins, a kinetic energy is stored in its rotating mass. If the motor is disconnected from the power source, it continues to rotate for a period of time until the stored kinetic energy is totally dissipated in the form of rotational losses. So in the dynamic braking method, remember we have three types of braking: regenerative braking, dynamic braking, and the other one is plugging. Uh, Plugging methods, right? So three types of braking. So in the dynamic or rheostatic braking, what you do is you're going to what you do, dynamic braking. What you're going to do is you let's assume you have okay. Let's assume you have a switch here. So this is a switch, and we have point A, point B. This is point A, this is point B, and we have your VT here. Okay, so the dynamic braking is whereby when you try to brake the motor, what it does is you change your switch here from A, the normal operation, you have A, isn't it? You connect to the terminal voltage. But in the dynamic braking, what you do is going to switch to point B. So you're going to disconnect, right? So you're going to disconnect the terminal voltage, and what left is only your motor and an external resistance here. So you have RDB, call it. You have a resistor connected in parallel with your motor there. Right? So if the motor is disconnected from the power source, it continues to rotate for a period of time until the stored kinetic energy is totally dissipated. So you still have the momentum here too, but after a few seconds or a few period of time, then there will be rotational loss, so the motor will be brake. So the faster the dissipation of the kinetic energy, the more rapid is the braking. So it depends on the size of the resistor here. Right? So if you uh, place a smaller resistor, then you can have more energy being dissipated. Good. Okay. Another method of reversal is dynamic braking. In this method of braking, the motor which is at running condition is disconnected. It's disconnected through. It's straight disconnect from the a source and connected across a resistance. Okay, so that's what happens here. So when the motor is disconnected from the source, the rotor keeps rotating due to inertia and it works as a self-excited generator. So when the motor works as a generator, the flow of the current and torque reverses again. When it works as a generator, the torque, of course, reverses as well as the current. With dynamic braking, the kinetic energy of the motor is transformed into electrical energy and dissipated in resistive elements. The rate of energy dissipation can be increased by the design of braking resistance. So it depends on the braking resistance, then you can control this, the braking, the rate of the braking here. So when the machine is connected to terminal A, it runs as a motor. So I just explained that. While the motor is rotating, it requires kinetic energy and stored in its rotating mass. The current IA flows into the machine. So in this case, current flows into the machine because it's in the motoring mode. Right? It is in the motoring mode. When we change, if the terminals of the motor are switched to position B here, we switch to position B, the energy stored in the rotating mass is dissipated in the braking resistance, RB or RDB, dynamic braking. This is possible when the machine maintains field, the braking current IB flows out of the machine. So now IB or I armature during braking. IB is actually I armature during the dynamic braking, IB here. Right? So I hope you do not get confused. We have any current here. So here IB or IDB dynamic braking equals to the armature current during dynamic braking. Okay, it's armature current. However, the machine maintains the braking current flow out of the machine. The smaller the resistor is, the faster the energy is dissipated and the faster the motor brakes. So if you replace with a small resistance, then the faster the kinetic energy will be removed and the motor will be slow rapidly during that time. Okay. So this is again dynamic resistance braking. Assume that the machine is running at speed of omega, then dynamic braking is applied. The terminals of the armature circuit are disconnected from the power source and connected across the braking RB. The field current, the field circuit is also disconnected from the armature circuit, but is still excited by the source. Under this condition, the back EMF EA is the voltage source of the armature circuit, and now the current is again IB equals to EA divided by RA plus RB. So if you do the KVL plus this equation, then you get this equation minus EA over RA plus RB. And again, you can replace K flux omega M. So the negative sign indicates that the direction braking is in the reverse direction of the armature current. So that is the meaning of that question. So the power dissipated during the dynamic braking is composed of two major components. The first is mechanical losses, which are due to the friction windage loss. The second component is electrical losses, PB or PDB, in the armature and the braking. These losses can be calculated as, I think, PB equals to, we start with the equation of omega T. Right? So we start with the, if you want to look at the losses, right? So you have PB equals to omega T, isn't it? We know that is omega T, and we know that this is equals to omega K flux multiplied by IDB during the braking, isn't it? Absolutely. And here, before this, we know that IDB equals to minus EA divided by RA plus RB, and therefore you can replace this dot equals to K flux B equals to K flux. So here you have I dB equals to minus K flux omega divided by RA plus RdB. So if you replace here, then finally you find out that your power PdB or PdB here equals to minus K flux omega squared divided by RA plus R. Okay, that will be the equation. PdB, the loss, equals to minus K flux omega squared divided by RA plus RdB. So that is the losses that we can look at. The equation here. Then look at this speed versus current. Okay, for that equation here equals to K flux over multiplied by omega divided by RA RdB. So if you have RdB is small, then you can get a higher current, isn't it? If you maintain at the speed, maybe I can go to the next slide. Next. So we have IA, IDB equals to we rather go on remove this flux omega. Okay, so we have this equation. So what does it mean? If RdB is small, sorry, if RdB is small, then we can get IdB is higher. Sorry. If you maintain omega, if you want omega here maintain at certain speed, I can draw it here. So you want to maintain omega at the same speed here. Okay. So therefore, if you reduce RdB, then you get a higher current, isn't it? Okay. Okay. This is the characteristic, top speed characteristic when you have this breaking. And during this time, you have a normal motoring mode. Remember just now, when we talk about the regenerative braking, this is the normal top speed versus top speed characteristic. So we have this 0.1, isn't it? Then we have this 0.2. But now in the dynamic braking, now you're going to have IA here. Sorry, IB1. The slope of the characteristic actually depends on the RB. So here you have RB3, RDB, RDB2, this is RB, and we have RB1 here, okay, and we know that RBDB1 is less than RDB2 less than RDB, right? So therefore, you have DB1, DB3, IDB2, IDB1. So the smaller the R, we have the a higher current. Okay, so that's the speed again current characteristic displayed here. The first quadrant of the graph is normal or motor position, where the motor is operating at point A. The figure shows the characteristic of for three different values. The smaller the breaker resistance, the larger is the braking current. So when the switch is in position A, the motor operates at point B, at point A. The armature current IA flows from the source to the motor. By connecting the switch to terminal B to do the braking, the voltage is disconnected and the resistance RB is inserted across the motor terminals. The operating point is level B for RB1. Understand that? You can read that. This current is flowing from the machine to the braking resistance. And that's it. That explains the dynamic braking. Again, I'm going to show you the one of the examples. All right. Any questions before we take a 5-minute break? Okay. Don't worry. I'm going to share the slide, the video recording afterwards. Don't worry. Okay, we take a 5-minute break. Then come back. Okay, we're going to continue in a short while. Okay. All right. Have a drink. All right, sure. We continue with counter current breakings. Remember, we have three types of three types of braking. The first one is regenerative braking. The second one will be the dynamic braking, and finally you have this counter current braking. Okay, so the direction of the rotation of electric motor is dependent on several variables. Among them are the phase sequence. So in order for you to control the motor, there are a few variables. That's what it says here. Among them are the phase sequence of the stator windings. As a three-phase AC machines, there are ABC phase sequence, or it can be ACB, isn't it? Positive sequence, ABC, red, yellow, blue. Or you can also have the negative sequence, which is red, blue, yellow, or ACB. Okay, so this will actually change the direction rotation of your motor. Next. All right, as shown figure below, if we reverse the sequence, so what happens is if you reverse the sequence of the three-phase system here, ABC, for example, we start with ABC and the rotation of the field wind flux. There is a magnetic flux that rotates in the clockwise direction. But once you change the sequence, the field or the flux density or the flux will rotate in the opposite direction just by changing the phase sequence. Okay, so now we have speed torque characteristic of under regenerative braking. This is the one that we discussed just now. We have torque, speed, and torque, and we have this is a motoring quadrant. This is a braking quadrant, and the load torque is assumed to be bidirectional. So if you have this case, you have the torque. We say that the torque, the load torque, is bidirectional. Bidirectional. Why is it bidirectional? Because it can be positive and it can be negative. So you have a positive torque here and you have a negative torque here. So this is known as bidirectional torque. Right? Depends on the torque. Okay. So next. Again, the same story. We have this uphill and downhill motion of the car and motor operation. Again, speed torque characteristic. Next, is it the same? How come it move to, sorry, it jump to the regenerative braking again. Okay, the direction of rotation of electric motor is dependent on several variables. If the power source is disconnected, when the motor reaches standstill, the motor is stopped by the counter braking. Right. If the power source is disconnected when the motor reaches standstill, the motor is stopped by the counter current braking method. So we can have this counter current braking method by changing the phase sequence, right? So your motor can also work at both directions. This is both are motoring mode, but here we have a positive omega m, which is follow the clockwise. And during this motoring or reverse motoring operation, so this is forward motoring. Here we have a reverse motoring sections, whereby your omega m now reverse the direction, anti-clockwise. Okay? Clockwise. Counter current braking is used to stop or slow down the motor or reverse its direction of rotation. This method is used in applications which require immediate stop application. It is a two quadrants for the steady state operation of two sequence. In each case, the machine is running as motor. So both are actually motoring function. So in the DC machines, when we talk about DC machines, the braking occurs when the terminal voltage reverses its polarities. Yeah? So when you reverse the polarity of the voltage, then you can have this counter current braking. But there are two types of counter current braking. The first one is a plugging, or by reducing the reduction of the terminal voltage. So reduce the terminal voltage, plugging. Or the other one is terminal voltage reversal. You directly reverse the voltage at the terminal voltage. Okay. So the plug-in method is suitable for the gravitational type load where the motor stop reverses direction, rotation operates under holding. The TVR is also a method that can stop the motor rather rapidly or reverse its direction. It cannot hold the motor at speed if the load is gravitational. Right. So this is to consider the plugging. Now, if you look at these situations, the load torque the load torque is unidirectional. Only one direction, which is toward downwards. This is your FL or TN. So the load torque or the force is only downwards. You consider this lift system, isn't it? And of course, your motor torque will be in that reverse direction here, or upwards, rather upwards. Okay, so that is your FM, the motor torque or the force. All right. The elevator on the left side of figure is moving upward, but the speed is bidirectional. Sorry. So your speed is bidirectional. I mean, the rotating of the motor here can be directional. Can be clockwise or, anti-clockwise or clockwise. It is bidirectional speed, depending on the motion of the elevator. So now, this is the plugging. So what happened is, this is a normal operation. Right? This is normal operation of your speed torque characteristic. Right? When you have Vt equals to V1. So the terminal voltage of V1, there is your normal speed torque characteristic. Right? But you can actually control the motor by reducing the voltage. Okay? So if you reduce the voltage to V2, now the torque speed characteristic move from that line to this line. Okay, so this is with V1, and now it changed to V2. So for a value of V2, you can actually move this characteristic downwards until you reach this particular point. So therefore, point 1 represent the outward motion of the elevator, the load torque is TF, and the voltage applied to the armature of the motor is V1. Okay, so now let's move on. Okay, one way to achieve downward operation is to reduce the armature V2. So this is, I'm going to write here so I can pass to you. So for plugging system technique, what you do is going to change, reduce the armature voltage to V2. Yeah, reduce armature voltage to V2. So therefore, now you are changing your torque speed characteristic or speed torque characteristic from the first one. You have a line here. There's no straight line. Okay. So from there, now it changed to your point. Okay, so this is with V1. Now you have V2 here. And V2 is less than 1. So, so if you want to maintain a certain speed, but in the opposite direction, okay, so this is your speed 1, operating point 1, motoring mode. And then if you want to change to 2, so you reduce the voltage there. You change to point 2, whereby you have the same speed, omega, because this is omega, this is torque, right? So, what you do, you reduce V2 until you reach this to here. So that's a normal version. And then you can read again. The operating point of the motor moves from 1 to 2. The motor does not settle at point 2 since the load torque and the motor characteristics do not meet at point 2. So it doesn't stop there actually. So you have to move. Okay, so this is point. Right. So this is load torque. Okay, the behavior of the motor there, it doesn't stop at point 2. Yeah? Once you change your voltage to V2, it goes to V2 at the moment, and it will not settle. Dia takkan duduk kat situ. It doesn't stop there. It tries to travel back to number 5 here. Because you have the same torque, isn't it? Okay, so this is the same torque. We talk about the same torque. So it won't go there. Now it travels back to 0.5 here. So while doing that, while traveling to 5, it will reach 0.3, it will arrive to 0.3, and will also arrive to 0.4 here. Okay, just try to understand that. So from there to that, the motor operating point moved from 2 to 5. But while traveling to the right, it passes through 0.3 and 0.4. So what is 0.3? 0.3 is where we have no load torque, omega naught. This is where we have torque equals to 0. While the is moved to 3, the motor is so during this region, this is known as regenerative braking. Okay, and then it travels to point 3, whereby you have no load torque operation. No load torque operation. So at point 3, the motor speed is equal to the no load speed, and we have discussed before because no load torque, so current is 0, so therefore you have omega 3 equals to V2 over K flux. Sorry, torque also 0, so you have omega 3 equals to V2. So this is the same equation that we had just now. This is point 3. Now it is V2. VT2 is denote voltage, the reduced voltage that we apply to the motor. Then we have now the operating point does not settle at point 3. It still travel. The motor still doing this from 2 to 3, and finally it goes to point 4. So if you look further, at point 4 here, you have omega equals to 0, isn't it? The motor stop and its speed is 0. So during that 4, you have omega equals to 0.4. And therefore you have this equation, the previous equation that we had, V2 divided by K flux RA over K flux squared, TSC, what is SC? Never mind. The torque equals to 0. So in this dumper, the motor operates in 3 quadrants. So if you look at this quadrant operation, the motor actually works under 3 quadrants. First quadrant here, and then it goes to point 2, the second quadrant, and finally it goes to quadrant number 3. So here you have omega m rotates in that direction. In this direction, omega equals to that direction. Here you also have the same 3. So when it goes into the quadrant 3, now the motor rotates in the opposite direction. Okay, this is still point 4. Then we move to point 5. The motor torque at point 4 is labeled TSC. The point here is SC and can be determined by this equation. TSC equals to K flux omega Y. Because just now we have equation of, we talk about omega 0.4. So you have the equation of omega equals to Vt over Ra minus RA IA divided by sorry. We have the equation of omega equals to Vt divided by K flux minus RA T divided by K flux squared, isn't it? So we have this equation, and at here you have omega m equals to 0. So here you have omega equals to 0. So this is 0, and therefore you have torque equals to 0.4. You have torque equals to K flux V2 to from that equation. Because omega m equals to 0. Right? So next is that's the operation. That's the operation of the plugging. And finally, when you arrive at 0.5, and here at this point, so now it goes back to the same equation, omega 5 equals to V2 divided by K flux, RA divided by K flux squared, and this should be greater than 0. So this equation should be greater than 0 because it's negative. Okay, so there's some of the equation involved. I'm going to let you read this total terminal voltage reversal. So the idea is you're going to change the direction. Just a matter of you simply change that direction. All right, the terminal, so from positive negative to negative positive, and that will provide the reverse braking. Hmm? The terminal voltage reversal, so you can read that. Right, so you can try, Simon. You can. This is not assignment, just for you to as an exercise. I get to. Our assignment will be actually on the simulation. eh. The only assignment that you need to do is do the simulation. All right. Okay. So now we're going to look at the example. One example. Look at this example. Let's do it together. Okay. This is okay. Right, question number one. With the aid of a suitable diagrams with labels, describe what are the four quadrants of operation of a motor drive. How does this apply to motor control system? So you can, I will share with you uh, some of the, you can actually you look at the Sharkawi books. And the four quadrants. Okay, you can try explain by using this Sharkawi books, right? Normally, we expect you to draw or sketch this four quadrant speed top characteristic. Okay, you must the diagram here should be drawn. Eh? So clearly state, I mean, draw the motor, the load, or you can have this uh, the load torque, and try to write assumption, do some assumptions, saying that uh, clockwise direction denotes the positive speed, for example, or positive torque, for example. So because we assume here the clockwise direction is positive. So we have positive quadrant, and next is we have a positive speed, negative torque. So omega is positive, m at the top, the motor torque is opposite direction, so it's negative. And in this case, we have both torque and the motor rotates at the same speed, but in the opposite direction. In the opposite direction. So you have negative torque, negative speed. And finally, you have positive torque and negative speed. So the torque clockwise, but the motor rotates in the anti-clockwise. Okay, so this is a four quadrant. Please read this as well as on the leaf operations. I'm not sure whether I put it here. So this is not leaf operation. I'm going to share with you one document on the leaf operations, whereby this is to explain the four. When we consider the leaf conditions, okay, to explain the four quadrants, it's best to use the leaf system. For quadriculation. So we consider a leaf application or leaf system. Okay, so if you leave a system, you assume that you have condition of right for quadrant and okay, whereby you have this is your leaf or car, your leaf lah, and this is your counterweight. Right, and this is your motor. So you can start with you may assume that you have counterclockwise as positive. Okay. Right. It's best to use this leaf system to explain the four quadrant operations. Now I'm going to share with you that particular, we call it the notes, and you describe that to this. So you need to consider you have a counterweight and leaf here. What happens if the counterweight is greater than the weight of the counterweight is greater or yes, greater than the leaf? For example, in the case of empty leaf. Okay. So what happens during this time? And then you have to understand in terms of before you apply anything. If you consider this situation where the counterweight here is heavier than the empty lift, what will happen? Of course, the car here will move upward, isn't it? And your counterweight here will move downwards. And if you talk about the motor here, this is your motor. So your motor will operate in that direction, isn't it? To start with. Okay. You have to consider the system without any external, the external intervention first. Look at the condition first. The condition when the counterweight is greater than the empty space. So what happens? Of course, you're going to feel okay the force or the torque to the system here, whereby your counterweight or the system here will move anti-clockwise. Okay. Right? So you consider that, and then you look at the load torque and also the load of the direction, which direction that you want to move the motor, the lift. Is it are you going to move upward or downward? Upward or downward? So here you're going to have upward or upward. Don't worry, I'm going to share that with you, and you need to understand that. Yeah, you need to understand that, inshallah. Okay, so next we move to the example here. Okay, so we have 500 volt power motor and with 45 kilowatt. Isn't it? So let's try to write it straight away. So your solution. So your motor here, you have 500 volt V E equals to 500 volt, right? And then your power equals to 45 kilowatts. So normally when you given this is the output power. And we talk about motor, so this is definitely the output power, which is equals to 45 kilowatt. Sometimes you'll be given in terms of HP, isn't it? Horsepower. So remember, 1 horsepower equals to 746. Actually, the accurate, the actual is 75. So 745.69 something. I can't remember. But normally we use 1 horsepower equals to 746 watt, isn't it? Okay. So sometimes you will be given in terms of horsepower. 50 horsepower, 25 horsepower. So you have to multiply by 746 to get this output power. Eh? So we assume that we have, of course, you know this. Eh? So if you are given in terms of horsepower, so you have to multiply by 746 to get the output power. And then you have 600 RPM. So that is the rated speed. Okay, so call it the N goes to 600 RPM. What else? It's a DC shunt motor. So quickly try to see the configuration, the circuit of the shunt motor. Ways, we have that. That is your VT, EA, this is IT, IA, IF. Okay. Of course, when we look at this drawing, of course, IF is maintained a certain amount because IF equals to VT divided by RF, isn't it? So the inductance doesn't affect the steady state value because the inductance L doesn't affect it because it's the DC operation. So we IF RF, right? So VF equals to IF multiplied by RF. And normally RF is very high compared to RA. So this is in terms of hundreds, and this is less than 1. Okay, less than 1 RA. Right? So in this case, we have the field resistance is the field resistance and armature resistance is 0.3 to 100. So we have RF equals to 200 and RA equals to 0.2 ohms. The field current is maintained constant. Of course, we have a constant current here. Therefore, flux depend on IF. So if IF maintained, flux also maintained. All right. The field current is maintained. Armature reaction and brush drop may be neglected. So you can armature reaction, EAR reverse motor, you can just neglect that. Calculate the rated armature current. You need to find what is the rated IA full load or IAR rated. Okay, so what is this? And hence find the speed under each of the following conditions at which the machine develops an electromagnetic torque equal to the rated. So you need to find what is omega dB, omega regenerative braking. So you just put RB, regenerative braking, omega plugging, B, and finally omega dynamic braking. Okay, so you need to find what is the speed, and you use the external resistor of 5.5 ohm, and then you have also 2.6 external resistor. For regenerative braking, you don't have any external resistor. Okay, so we try to do some solve this problem one by one. Okay, so we start with the motor input current. So we know that, and what else? Efficiency, I forgot to write this. We have the efficiency equals to 90% or 0.9. Okay? So we start with the uh, uh, efficiency. We have efficiency equals to P out over P in, isn't it? Of efficiency is always defined by output power divided by input power. So that gives you P out. We know that the value is 45 kilowatt divided by what is the input power? Of course, from VTI T, isn't it? So VT will be no, you already given VI V multiplied by I. Okay, so that gives you you need to find IT first. So IT equals to equals to 0.9, and therefore you have IT equals to 45000 divided by 500 multiplied by 9. You okay. So your terminal current actually equals to 100 amps. Okay, 100 amps, super, right? And therefore you can find the next is you need to calculate for IF. IF equals to VT divided by F. So that gives you 500 by 200. That gives you right, 2.5 amps. Right. So next is we know that armature current IA full load is to I. So we have 100 amps minus 2.5 amps. That gives you 97. Okay. Right. So next we look at the speed. You are given in terms of RPM. Is it? N equals to um, here we have 600 RPM. Now you change that to omega, so that become 2 pi 600 divided by 60. So 60. So that gives us 62.83 radian per. Okay. Then we have the equation of E A equals to VT minus IA. Therefore, that gives me 500 minus IA is 97. RA is 0.2. So that gives me 480.5. So that is the back EMF. And now we also like to look at the coefficients. And we know that EA equals to K flux multiplied by the M, isn't it? So let's say K flux here equals A. Yeah. And the unit is what? K flux. So K flux here, you look at the unit, that would be voltage per radian per second, isn't it? So it is voltage per radian per second. Just follow this voltage per radian per second. So that gives you constant. And because we know that flux IF constant. Isn't it? So this term doesn't change at any point. So we replace with K there. So here you have K equals to 480.5 by omega m, that is 7.65. 7.65 voltage. Okay, right. Then we know that torque, electric torque equals to K flux. Remember just now we have torque equals to K flux by IA, isn't it? So here we have replaced this with K, so it's K multiplied by this 7.65 by 97.5. 7.5, that can be 745.9. Okay, and then you also have this is electric torque, torque per machine, motor electromagnetic torque. Then we have this nominal shaft torque, right there. This is so, current. Then we have this next is nominal shaft per motor. This is given by output torque P out equals to P out over omega. Remember, we have this equation. So P out is by that gives 7.6. Next is no load torque equals to electromagnetic torque there minus with the output power. Okay, so you have the torque K flux omega here 745.9 minus 716.2 minus the out. Okay, so it's 2 29.7. Okay, so this is the uh, no load torque, right? And finally, yeah, yeah, no load torque. And therefore, finally, you have this electromagnetic torque equal to the rated value. So it's torque I equals to E plus plus E. So that gives the total electromagnetic torque of 775.6. 7475.6 Newton meter, 39.7 Newton, 716.2. Okay, so once you get that, electromagnetic torque equal to the rated. So this is the torque that we need to consider during the braking. Okay, so first we have the condition whereby you have regenerative braking. Regenerative braking. Okay, the regenerative braking. So we have torque during that. T call it as a TRP equals to EI here. Okay. And from the equation before, you have omega RP equals to Vt for K flux plus TRB multiplied by Ra over K flux squared. Okay. So if you do that, you can insert or replace with the result that we have just now, and that gives the equation to 93.7373, and it's best for you to convert that into RPM. So this is in a radian per second. Okay. Then you can find that the RP equals to 891 point oh, okay. 650 point RPM. So you calculate that, and that gives 61650 R. Right? Remember, just now we have omega. You still remember the top speed here. So we have 0.1, 0.2, 0.33. So point here, 0.1 here, you have 600 RPM. And now, during regenerative braking, you have 650 RPM. Slightly higher than the speed at omega 1, condition 1. Point number 1, so we have point here. You can also calculate for point number 2. And so that's why the speed during the regenerative braking is 650 RPM. And then we look into the part B, which is the plugin. So again, we replace with so we look into the plug-in current. I P equals to top plug-in divided by K, isn't it? Remember, top equals to K flux I. So we replace that with K. Cp divided by K. So that gives me 101.4 here. And the total resistance, we add 5.5, isn't it? So the total resistance R P here equals to RA plus, or rather than Rx equals to RA plus RP plugging. So that gives me RA is 0.2 plus 5.5, 5.7 ohm. And then now you use the equation whereby you have omega P plug-in equals to IP1, I plug-in 1, IP multiplied by R, which is R here, Rx, divided by K minus VT divided by K. Now you use this equation. Okay. So minus. So you have that. session. Calculate for that, and finally you have NE equals to 2 pi over 60 multiplied by omega p. That gives you the answer 97.3 RPM. Okay? 97.3 RPM. So that is a plugging RPM. And finally, if you have this dynamic braking, so again, you need to have your torque dynamic braking equals to Ti equals to 5.6. And we calculate for R first. Rx equals to 0.2 plus with 2.6. And now during dynamic braking, you have omega dB equals to only top dB multiplied by R divided by why? Because you remove the Vt equals to 0. So this equation, previous equation, Vt divided by K flux K minus or plus T dBr over K2. So you just consider the second term because Vt over K flux is equals to 0. So you calculate that, then you have N dB equals to 354.4. Okay, so that's for the dynamic braking. So that's one example. You can do the more example from the books, right? Okay, any questions? So just give you one.
Prof,
Yes,
boleh minta gak slide?
boleh boleh. I will give you all these notes
Oke, sir.
on together with the recording, our recording session. Okay, is there any more questions?
No, sir.
All right, great, great. Okay, inshallah. We have another 2 weeks before our semester break, isn't it?
Yes.
Yes. Okay. So I'll try to do more video, or I can share with you some video regarding the operation of the drive, everything, and just check your announcement, in the WhatsApp or Google Classroom. Okay. All right. Thank you. So we have about 20 students, 22 students. I can trace from the Excel. Some of you may disconnected, come again. I can see some of you left, then come again. That's probably because of the connection, isn't it? Internet connection. No problem. Okay, everybody, enjoy holiday, public holiday. Enjoy yourself. Go and have a break. Okay, see you on Friday, inshallah.
Thank you, sir.
Assalamualaikum.
Thank you, sir.
Okay,
Thank you, Prof.
bye.
Thank you, sir.
Thank you.